All right, so final exam review only today. Hopefully you had a chance to look over the sample exam posted on Canvas. So the plan, after all, is to have 3 questions on the final exam. And they will be one on each of the following topics. Inner product spaces will be one topic. And that would include checking that a given map is an inner product, or looking at adjoints, self-adjoint operators, normal operators. Or just looking at, the value of the adjoint of an operator at a given point. Also, positive, definite, or semi-definite operators and matrices. So that, I think it's part of chapter 6 entirely. Well, in fact, the exam will cover chapter 6 and 7. The singular value decomposition for linear operators and for matrices. And 3, the Jordan canonical form. Now, if you looked at the sample problems, you're going to see that in the question with the Jordan canonical form, you're also asked about diagonalizability. They are actually related, as you probably noticed last time in the examples that we've seen. So sometimes it's useful to find basis for the eigenspaces when you look at generalized eigenspaces. So even though the exam doesn't specifically cover chapter 5, which is about diagonalizability, I would say that is part of understanding what's going on in 7. So review that as well, diagonalizability. So 3 questions, probably about 4 subparts each. I've been asked whether it's possible to have like a bonus part or a bonus question, and that might happen. So maybe there will be 5. Some questions might have 5 subparts, and one will be like an extra something, extra points, let's say.
Like if you do all 5,
you'll get more. No, a specific one will, so probably it's going to be a bit more difficult or something, making you to go further into that.
So there would still be 3 questions?
3 questions, each of them probably around 4 subparts, but maybe some of them, there might be a 5th subpart to some of them.
Yeah, it's extra.
Yeah, extra. Okay. That's pretty much it. So what questions do you have from the sample? So those questions actually have been given to previous final exams or comprehensive exams in the past in the department. So that's the type of question that you would see on a comprehensive exam.
Have you posted the solutions to the final and to the suggested problems?
To the final, not yet. I thought we were going to discuss it today. The suggested problems, again, not. No, I haven't posted them, but I can do that. What's the day? It's Wednesday, so probably by Friday I should be able to post both. But if we go if we go over this today, and unless there are only specific questions that you have, I don't know, how do you want to go about this? So, do you have a copy? You don't? Okay, let me try to, without messing up everything here, let me try to get it. All right, so question 1. So part A, show that a given map pair is an inner product, right? So how do you show that something is an inner product? What do you have to check? Okay, first one, it has to be linear in the first. So if you do something like F1 plus F2, inner product, sorry, with G, you should get the same as this. And that shouldn't be too hard to do, right? Because it's just the integral of F1 plus F2 times G, which turns into the integral of F1G plus the integral of F2G, and here it is. Second property. CFG should be the same as C times the inner product between F and G. It's an inner product, it's a vector space over R, so for any scalar C in R. Again, that would mean the integral of C times F times G, and C, the scalar, can be pulled out of the integral sign, so straightforward. What else? If you switch the order you should get the complex conjugate.
Or in R.
We're in R, so here it would mean switching the order doesn't change anything, and it doesn't because it's the integral of the product of the two functions. So, and 4, the inner product between f and itself is strictly positive for any non-zero function. So that would mean the integral from -1 to 1, f of t times f of t, so f squared of t dt. Well, it's a function that is non-negative, right, f squared, so its integral is non-negative, but still it could be 0, so why isn't it 0 unless f is 0? Well, the good thing is that it's P1 of R, right? So it's not a big deal to actually see what f squared looks like. F of t is just some at plus b, after all. So f squared is what it is. And so when you integrate f squared from -1 to 1, what happens? Turns into this, right? This one here will become 0. So that would be the integral of f squared of t, which is greater than or equal than 0, but when is it 0? Well, it can only be 0 if a and b are both equal to 0. That's the only case, right? Which basically means that f is identical equal to 0 as a function. Right? All right, so now part B, we're considering an operator T on this space, which is f prime plus 3f. And you have to find the value of the adjoint of T at this function, and then answer the question whether T is self-adjoint or not. So how do you find T star of 4 minus 2T? You have two options, right? To find the value of the adjoint. You can find the formula for the adjoint in general. How do you find that? With a matrix, right? You find the matrix of T in some orthonormal basis for P sub 1 of R, which, as I said, if you ask me for the orthonormal basis for any space you see on the exam, I'll give that to you. So you find the matrix of T in some orthonormal basis, then you find the matrix of the adjoint in that basis, and based on the matrix, you can find the whatever value they're asking for. That's one option. What's the other option? Just computing it using the definition of the adjoint, that thing with T of the inner product between T of F and G is F, and the inner product between F and T star of G. So which one do you want to see, if any? The thing with the matrix? Okay. Okay, so if you want to find the formula for T star in general, you're going to need an orthonormal basis for P sub 1 of R. The standard basis is 1x. And you can go through Gram-Schmidt and so on, normalizing all the vectors. to get an orthonormal basis, which I think it was this. Let me make sure I'm not. Yeah. So this is the orthonormal basis for P sub 1 of R. And T, what was T? T was F prime plus 3F. So the matrix of T in that basis, so when you apply to the first vector, which is 1 over the square root of 2, you get 0 plus 3 times 1 over the square root of 2. So the first column is 3 and 0. Right? 3 times the first vector plus 0 times the second. When you apply T to the second one, this is the derivative, and then plus 3 square root of 3 over 2x. So when you want to write it in that basis beta, you're going to get square root of 3, right, times the first vector, plus 3 times the second vector. Okay, so the matrix, because this is an orthonormal basis, we have this property, right? That the matrix of the adjoint of T in this basis is the adjoint of the matrix of T in this basis. You just take the transpose, basically, because we're over R here. And because you got two different matrices, you can already conclude that T is not self-adjoint. Because that was part of the question there. Now, of course, if T was self-adjoint, it would have been much easier, because then T star of 4 minus 2T would be the same as T minus 4, T of 4 minus 2T, so that would have been simpler. Since it's not, what are you going to do? Well, T star of 4 minus 2T as a vector in the basis beta is the same as the matrix of T star in the basis beta times the coordinate vector for 4 minus 2T in the basis beta. So the matrix of T star in the basis beta is 3, 0, square root of 3, 3. What about 4 minus 2T? Or 4 minus 2x to keep the same variables. So 4 minus 2x in the basis beta is 4 square root of 2, right? Times 1 over the square root of 2. Minus 2. Square root of 2/3 times the square root of 3/2 x, right? And that's the vector in that basis. Multiply them. And that's 12 square root of 2. And 4 square root of 2 times the square root of 3, so 4 square root of 6 minus 6 square root of 2 over the square root of 3. Okay. And this is what? Isn't that 2 square root of 6? The 6, I'm trying to simplify here. 6 is 2 times the square root of 3 times the square root of 3, right? So 2 square root of 6. So overall is 2 square root of 6. All right, so that is the beta coordinate vector of what we need. What does that mean? It means that t star of 4 minus 2t, or 4 minus 2x, is this first entry, 12 square root of 2 times the first vector, right? Plus 2 square root of 6 times the second vector, which was the square root of 3 halves. X or t, just to keep the same variables. So 12 plus 6k. Yeah.
If we want to do it this way, would you give us the orthonormal basis?
Yes.
Or do we have to do that?
No, I'll give you the. But I doubt I'll type the exam by, at every point saying I'm going to give you a space and then immediately give you the orthonormal basis. Probably it will not happen. So what will probably happen is as you sit in the exam, you just ask, I need an orthonormal basis for whatever. Or, or maybe make a list somewhere at the bottom of the exam with the standard orthonormal basis for the most famous spaces. Yes.
You can ask one method in a class. Gx, y, the inner product equals to the average of t sugar y.
I don't get it, sorry.
She's saying that you gave us the other way to do it, not using it.
That is correct. I was telling you that we've
Both of
seen,
them are correct.
both are correct. Yeah, I just wanted you to see the other option here. Honestly, I think I might prefer this option, especially if this one here, especially if you're also asked whether t is self-adjoint or normal. When you have to answer that question, you have to find the matrix anyway, so it would be like double the work to go in both directions. All right, so now C and D have nothing to do with the questions above, so they are more theoretical in nature. If T is self-adjoint, then the inner product between T of x and x is a real number for every x in V. How would you do this? You need to look at the inner product between T of x and x. Itself, T is given to be self-adjoint, so that makes me think about moving T into the other entry. According to the definition, this is the inner product between x and T star of x. But again, T is given to be self-adjoint. So that's the same as the inner product between x and T of x. So what did we get? That it's okay to switch the entries, right? But we know that in general, switching the entries means taking the complex conjugate, right? Since here it doesn't matter, the number is the same as its complex conjugate, that means it has to be a real number. And part D is backwards. if this inner product is real for every x, show that T is self-adjoint. No? What is T star? Well, T star is that operator with this property, right? And I'm saying that operator because it's unique, right? With this property. However, for our operator T, because this inner product is real, switching the entries is okay, right? Because there is no complex conjugate. So for this operator T, on the right side we have this, and by the definition of T star we have that, right? And T star is unique. So that has to be it, right? T has the property that T star should have. So what those examples mean are that you might see more theoretical questions, but they shouldn't be very lengthy or anything. You know, it is just to show some understanding of the basic things here, nothing too complicated. Okay. Let me go back and take the second question there. Okay. So this is about the SVD and the positive definite idea. So how do you find the SVD? What do you do? So this is the computational part, this one here, part A. So the singular values of a matrix are given by the, well, are the singular values of the left multiplication by A, first of all, right, operator. And you find those by looking at A star A, the matrix A star A, and taking the eigenvalues of that matrix, right? You just take the strictly positive eigenvalues and take the square roots of those. Those would be the singular values. So in this case, A star A looks like this. And you have to find its eigenvalues, so determinant of that matrix minus T identity. So do you want me to work through all the computational thing, or you think you can? Yes? Okay. I was afraid of that answer, and that's why I'll take a shortcut.
Shouldn't the 2 minus 2 be?
It should, yeah.
Yeah.
Is that 2 squared minus times 6 minus 2.
All right. T squared times 6 minus T. Okay. Nice. All right. So now we have 3 eigenvalues in decreasing order. Lambda 1 is 6 and lambda 2 and lambda 3 are both 0. So that gives me one singular value, right? You only take the strictly positive ones. So singular values are positive. Sigma 1 is square root of 6. And then remember that the SVD comes, so wait a minute. So first of all, what is sigma, that matrix? Because the SVD for a matrix gives you, in the end, 3 matrices: the matrix U, the matrix sigma, and the matrix V. The matrix sigma has the same size as A. A is a 2 by 3. And you start in the corner with the singular value that you have, square root of 6. And then fill in the matrix with zeros, because there is nothing else you can put in. Okay, then the matrix U, so then you think about L sub A. A is 2 by 3, so it's applied to F3 with values in F2. Right? So then you need to find the basis U1, U2, U3, orthonormal basis for the first space, and V1, V2, orthonormal basis. I think it's backwards, the notation in the book. I don't want to mess you up. Right? Isn't it V1, V2, V3? Let me just check. Not that it matters, but just to follow the notation from the book. P of VI is sigma I UI, so it's backwards. All right, so what are the vectors VI? Those, you get them from the eigenvectors of A star A over here, right? T star T in general is a self-adjoint operator, will always be diagonalizable, right? So you'll always have all the eigenvalues that you need and as many eigenvectors as you need. There will not be any problems there with that matrix. So how do you find them? You start with lambda 1 equals 6. So you look at the null space of A minus 6 identity. Not A, sorry. We're doing all this for A star A, right? Null space of A star A minus 6 identity is the null space of -4, 2, -2, 2, -4, -2, -2, -2, -4. So do you have the 2 vectors that you get out of this? Do you have them, the vectors?
No.
Wishful thinking. Okay, so let's find them. I hope you're going to see if I make any mistake here. Or that, if you have it. Six had multiplicity 1. I don't know why I was expecting 2 of them. X1 is free, so the vector looks like 1, 1, negative 1, if I did the right thing.
That's
No?
because I got that x1 is negative x2, and x2 is negative. So I think it was great.
But it doesn't matter. Isn't that negative 1, negative 1, 1, what you got as a vector?
I did the reduced rational.
Yeah. No. But what I'm saying is that if x3 is negative x1 and x2 is negative x1,
And no, x2 negative x3.
okay, then you have negative 1, negative 1, 1,
Yeah.
which is just negative 1 times my vector, which is fine. It's the same thing. You can use any scalar multiple, right, of the vector that. Okay. So this is V1. This one then should produce 2 vectors. Null space of A star A minus 0 identity. The third one is just the same as any of the first 2. Right, because it's just negative 1 times that. Okay. I want them to be orthonormal, by the way, V1, V2, V3. And just as they are not. So instead of V1, I'm going to do V1 times 1 over square root of 3 to make it of length 1. That's the problem. V2 will be times 1 over the square root of 2. And same for V3. So the matrix V is that was V1, and then V2 and V3. Okay, so now to find the vectors, how many do I need? I need U1 and U2, right? Basis for F2. We're over R here. So U1, U2. U1 we get them from V1 through the through L sub A and the SVD theorem. L sub A of V1 is sigma 1 U1. L sub A is left multiplication by A, and sigma 1 I think was what? Square root of 6? Square root of 6 times U1. So A V1 I'm not going to do that. Okay.
Is it A times one or A star A times
No, it's T of V1, and T, our operator, is left multiplication by A, right? So it's just A, not A star A. That's a good point. Now we're going back to the operator in the SVD theorem. So 2 plus 2 minus 2. So U1 is 1 over the square root of 6 times all that. So 1 over 3 square root of 2. 2, negative 2. So basically square root of 2 over 3, 1, negative 1. There's something I don't like here, and I already see why I don't like it. I said it's AV1, but the matrix that I wrote here is definitely not A. And now I go back to your question. No, I thought you were just asking in general. I didn't realize that I put A star A here. I'm not multiplying by this matrix, am I? I said I'm multiplying by A. What was A? And how did I realize it was something wrong? U1 has to automatically be a norm 1 vector, and what we got here is definitely not. So something was definitely wrong. All right. Matrix A was 2 by 3, right? So it's a 2 by 1 vector. This times V1, and V1 is this one. See? Good point. Because it didn't work again. Right? Still didn't have norm 1. Okay. And still square root of 3, right? Yeah, because it was the norm. Okay. Let's try it one more time. 3, 3. So U1 is 1 over 3 square root of 2. Which is good, right? Because the norm of 33 is the square root of 18, which is 3 square root of 2. It's good. It has norm 1. Okay, and that is the extent to which the theorem helps us, right? We need to come up with U sub 2. How do you find U sub 2? Well, can't you just find the vector that is orthogonal to this one and has norm 1? We're in R2, it shouldn't be that bad. What about 1, negative 1? That works, and it has norm square root of 2, so let's normalize it so I get an orthonormal basis. We're doing this on R2. Let multiplication by A goes from R3 to R2. On R2, you just do x1, y1 plus x2, y2, the standard inner product. Okay. Show that all the eigenvalues of a positive semi-definite operator are non-negative. Positive semi-definite operator, remember, that's a self-adjoint operator with this property. The inner product between t of x and x is greater than or equal than 0 for any x. You have to show that all the eigenvalues are non-negative, so let lambda be an eigenvalue. Again, that would be a more theoretical kind of question, but don't expect too long of an answer. So it's just going to be kind of straightforward, because if lambda is an eigenvalue, then if T has an eigenvector corresponding to it, right, a non-zero vector such that T of V equals lambda V. But then when you write that inequality above for x equal to V, you end up with lambda norm of V squared, and then because T is positive semi-definite, lambda norm of V squared has to be greater than or equal than 0, where V is a non-zero vector, right? So the norm cannot be 0. So the only way in which this is possible is when lambda is greater than or equal than 0. It's an argument that we've probably seen a couple of times already in the lecture, so it should be familiar by this point. C. Any positive semi-definite operator on a finite dimensional inner product space is diagonalizable. Now this, I don't know if we've seen it written exactly like this before, but there is not hard to see because this we've seen before. If an operator is self-adjoint on a real inner product space or normal on a complex inner product space. But being self-adjoint is automatically normal anyways, right? So a self-adjoint operator, for a self-adjoint operator, there will always exist an orthonormal basis of eigenvectors. That's the format in which we've seen it in the lectures. The existence of the orthonormal basis of eigenvectors means exactly that T is diagonalizable, right? So just having to go through the self-adjointness. D. Give an example of a non-trivial positive semi-definite matrix. By non-trivial, I mean not the zero matrix or the identity matrix. So you need a matrix that is self-adjoint, right? And at the same time, you need all the eigenvalues to be non-negative. That's what describes being positive semi-definite, or a matrix. And that, I think, we proved in class. And if I look at this description, it's pretty easy to come up with an example that is non-trivial, one without any kind of computations. Just take a diagonal matrix with a bunch of non-negative diagonal entries, so you automatically know that the eigenvalues are 2, 3, and 5, non-negative, and being diagonal is automatically self-adjoint, right? So both conditions will be satisfied. Right, so this one is self-adjoint. And the eigenvalues are 2, 3, and 5, so non-negative, so you're done. E. If A is positive semi-definite, then the singular values and the eigenvalues of A are the same. That, I think, we proved in class. But let me just remind you how it worked. So to find the sigmas, the singular values of A, you have to look at A star A, right? And compute the eigenvalues of A star A. But A is positive semi-definite, so it's self-adjoint. So the eigenvalues of A star A are the eigenvalues of A squared. And the eigenvalues of the square of a matrix are the square of the eigenvalues of the matrix. That's something from, I don't know if we talked about this year, or if you've seen that in the undergrad linear algebra, but it's not hard to check. Because if lambda is an eigenvalue of A, if you go ahead and multiply by A both sides, replace again AV by lambda V. Here it is. Same eigenvectors, right? For A squared by the eigenvalues now are lambda squared. And this can be extended, right, to any power of A. All right, so to find the singular values of A, you need to find the eigenvalues of A star A, which are the squares of the eigenvalues of A. But to actually find sigmas, you have to take the square root, right, of the eigenvalues of A star A. When you take the square root of the eigenvalues of A star A, when you take the square root of the eigenvalues of A star A, you just end up with eigenvalues. Okay. There are no negative numbers, right? So everything makes sense. We don't have to worry about complex or negative reals here. Okay. So this is the end of question 2.
Confused about
Yeah.
how we ended on part A. So did you respond U1, U2, U3, U1, U2, and U3?
Yeah, because, I mean, those two you have to put together in a matrix. Because the SVD for matrices means finding 3 matrices, a matrix sigma, which contains the singular values, and matrices U and V, such that A equals U sigma V star in the end. Okay, but that's how you construct those matrices. Yeah. No, I mean, in general, what's important to know is how to find the numbers, the singular values. But, you know, if they want you to find the entire picture with the vectors, it means the rest.
So in what case would we do that, the determinant like IJK?
When you have 2 vectors and you need a third one, you're missing a third one, then you take the cross product with the determinant of IJK. Here we had 1 vector and we missed the second one only, so it was easy to come up with a second.
Okay.
So it has to be, the space has to be at least R3 to make sense. To look at the cross product.
So like the example we did in class when it was just this, but
it was backwards, yes.
That's how we had to do that?
Yes.
Okay.
Because if you do it backwards, it's going to go from R2 to R3. So you're going to miss a lot of vectors from R3 depending on how many you can actually move over from R2 on, you know, the number of non-zero singular values.
Okay.
All right, so we're down to question 3. Which is computational only, I would say. So part A and B, you have to find basis for the eigenspace E lambda, and part B is it diagonalizable. That's something that was covered by midterm 2 after all, but it's going to be related to this. C, D, and E, well, actually C is the important thing, right? Finding the basis for each generalized eigenspace and then the Jordan blocks. Now, the thing is that what I'm going to have to do today is the teaching evaluations, because I completely forgot about that. And if we start this, it's definitely going to take us more than 15 minutes to compute everything. So what I'm planning to do, since, I mean, honestly, I think it's purely computational, this one. There is nothing tricky about it. You can just go ahead and work on it on your own, and I can attach solutions to the, you know, the suggested homework or anything. I can post my own version of the computations, which I cannot guarantee is going to be perfectly correct. Hopefully it will be, but anyways, computational only, number 3. And ignore those point assignments. So again, those problems were taken from various exams, so it's not like some of them had points attached and some. This is probably from a comprehensive exam. Because in a comprehensive, they come with 50 points each question. I see they add up to 50, so it's exactly a comprehensive exam question. So. Okay.
Can you explain the relationship between the diagonalizability and what we were going to do in 3 real fast?
Sure, sure. So if it turns out that a matrix is diagonalizable, or a linear operator, say it has, let's say, 3 eigenvalues. Three of multiplicity 1. and 1, the eigenvalue 1, has multiplicity 2, right? If A is diagonalizable, then that pretty much means there exists a basis of eigenvectors, so there exists a basis such that the matrix in that basis looks like a diagonal matrix, right? Or the matrix of the operator, if this is about an operator. Well, if you think about Jordan canonical forms, so for lambda 1, there is the eigenspace, E lambda 1, right? It has dimension 1. There is no other dimension that it can have because the multiplicity is 1. But then there is a generalized eigenspace which has dimension at most the multiplicity, which is again 1. So E lambda 1 and K lambda 1 are one and the same, right? So that means if you go through the Jordan process, that's going to produce a Jordan block 1 by 1. Okay, so if you look at the Jordan matrix, and you start with the eigenvalue 3, that's the first block, right? It's a 3 by 3 matrix. The first block is that just 3. Now, if you go to the second one, the dimension of K lambda 2 has to be 2 because it equals the multiplicity of the eigenvalue, so it has to be 2. But remember that you asked about the connection with diagonalizability. So if the matrix A would be diagonalizable, then the dimension of the regular eigenspace, E lambda 2, would also be 2. Because that was the condition, right, for diagonalizability. So that means, again, that E lambda 2 equals the generalized eigenspace, K lambda 2. Right? E lambda 2 then must have a basis consisting of 2 vectors, so 2 eigenvectors that are linearly independent. So that means for K lambda 2, there are 2 cycles of length 1, right? Because there is an eigenvector in each. If there are 2 cycles of length 1, each cycle of length 1 will produce a 1 by 1 Jordan block. So the Jordan matrix is the same as the diagonal matrix that you obtain through diagonalizability, right? So it all ends up being the same nice picture as before, but again, provided that A is diagonalizable. The same matrix A with the same numbers, if it wouldn't be diagonalizable, then this would change. Right, so instead of 2 1 by 1 Jordan blocks, you'll get a 2 by 2 Jordan block with 1 1 on the diagonal and the 1 on top. Right? Okay.